Hello students, continuing in the chapter of atoms, in the second lecture today, let us discuss X-rays and some of the leftover topics like electric discharges through gases. So let us begin with X-rays. What we are talking about is a kind of event of the year around 1895. The German physicist Röntgen bombarded electrons on heavy metal target the heavy metal target which was taken that time, that was say molybdenum, and X-rays were produced. You understand, this is the kind of event which took place in the year 1895, but that time we were not knowing that X-rays are getting produced. It was a time when a culture of bombardment was started, and it is continuing till date. If you are talking about hadron colliders, they are essentially deriving the kind of inspiration from this event, which you can say one of the first events in our scientific development. That time, whatever molybdenum target was taken and electrons were being bombarded on that, around that target we had several detectors, say electric field, say magnetic field, some photographic plates. It was found that there was no indication from electric or magnetic field, but the photographic plates which Röntgen was keeping around the target, that photographic plate was all the time getting exposed, and he was not in a position to discover what is the reason that that photographic plate is getting exposed. He was sure about this fact that some of the rays are definitely existing in that particular room, and as you happen to say in the algebra that let us suppose the unknown is X, so he named that let us suppose the unknown ray is X-ray, and later on the same name remained to this particular ray. His student Coolidge, provided a formal setup to the X-ray experiment, and in fact till date for all medical applications wherever you have a system from which X-rays are coming out, it is based on the kind of design Coolidge has provided to the X-ray production. And maybe in the exam you will be given this kind of terminology, Coolidge tube experiment. The meaning of Coolidge tube experiment is that it's a kind of, you can say, formal setup in which we have X-rays getting produced, and what Coolidge had done is something like this. You see, he took a glass tube inside which he kept this heavy metal target. As we said, this is, let us suppose, molybdenum, and here you have a coil which is getting heated, and because of which some electrons will be produced. If you try to remember, we had said there are 4 ways in which electrons can be emitted. One of them was thermionic emission, if you remember, in which you are heating up a metal and electrons are getting emitted. The other ways of emitting electrons, that was photoelectric effect or primary emission, secondary emission kind of thing. But here, by way of thermionic emission, we are producing electrons, and these electrons are getting accelerated. We may ask you the question, the kind of order you have to maintain for this accelerating voltage. This is in kilovolt, around 20 kilovolt, 30 kilovolt. This is the kind of voltage you have to provide to all these electrons. Now try to see what will happen. In case these electrons are produced and it is being accelerated through this potential, then you should understand that all these electrons, they are hitting the target. And after that, we are finding that X-rays are getting produced. This is the kind of mechanism he had for the production of X-rays. Maybe inside the target you can have some cooling coils, because when electrons will be hitting it, so automatically this will be getting heated up because of the collision. Understand? Collision की वजह से ये electrons जो target को hit कर रहे हैं, it may get heated up, वो melt ना कर जाए. You understand? To avoid the melting, यहाँ पे inside आप कुछ cooling coils रखते हैं, and finally these X-rays are getting produced. This is the kind of mechanism. Now, if you consider the range of wavelength of X-ray, then you should understand that range of wavelength of X-ray is somewhere in between, you can say 0.1 angstrom to 100 angstrom. You understand? This is the range. If you remember the hydrogen spectra we discussed in the last lecture, you had seen that Lyman series fell in ultraviolet region, and the order of wavelength for ultraviolet was somewhere around 900 angstrom, around 912 and so on. Now you can see the X-rays are having a wavelength slightly lesser than that. That means the X-rays, they are having larger energy, and to have the larger energy you had to have the target of heavy atomic weight. If you remember Rydberg's formula, we had used 1 by lambda proportional to z square. So if you want lower lambda, then you will have to have higher atomic number, and because of which the target you have chosen here, that is of high atomic number. You understand? So ये हमारी पूरी setup थी. Now you have to understand why this X-ray is getting produced and what are the types of X-rays we are having. At this context, let me tell you that if you have lower wavelength, that means the energy will be large, and they are called hard X-rays. Understand? हम एक term use करते हैं hard X-ray, and दूसरा term हम use करते हैं soft X-ray. Hard X-ray means they are of high energy value. You understand? हार्ड एक्सरे किसको कहते हैं? जिसकी एनर्जी ज्यादा होती है. जनरली आप एक्सरेज वगैरह देखते हैं तो एक माइंड में पिक्चर बनती है कि मे बी फ्रैक्चर डिटेक्शन के लिए वी विल बी यूजिंग एक्सरेज. देन रिमेंबर दैट इट इज नॉट ओनली द ह्यूमन बॉडी इन विच फ्रैक्चर डिटेक्शन वर्क इज डन, रादर इट इज ऑल्सो द स्टील स्ट्रक्चर. मे बी कोई ब्रिजेस हमने बनाई हुई हैं, उन ब्रिजेस में कोई क्रैक्स डेवलप हो रही हैं, उनको डिटेक्ट करने के लिए भी हम एक्सरेज यूज करते हैं. So there you will be using the hard X-ray. But अगर हमें लो एनर्जी की एक्सरे चाहिए तो दैट यू कॉल्ड सॉफ्ट एक्सरे, एंड सॉफ्ट एक्सरे आर ऑफ लो एनर्जी. सो इन केस आई आस्क यू लाइक व्हाट इज द वेवलेंथ ऑफ सॉफ्ट एक्सरे एंड हार्ड एक्सरे, देन यू मस्ट से दैट अगर ये वेवलेंथ इस रेंज में होगी 0.1 एंगस्ट्रॉम, 1 एंगस्ट्रॉम, सो दीज आर दी वेवलेंथ्स जिसमें एनर्जी ज्यादा होगी एंड दे विल बी कॉल्ड हार्ड एक्सरे. बट इन केस दी वेवलेंथ दैट इज लार्ज, मे बी 100, 10, 100, दीज आर दी वेवलेंथ्स फॉर विच यू विल से दिस इज दी सॉफ्ट एक्सरे. तो अगर ह्यूमन बॉडी से रिलेटेड फ्रैक्चर हमें डिटेक्ट करनी है तो वी विल बी यूजिंग द सॉफ्ट एक्सरे. बट इन केस वी हैव टू हैव दी fracture detection for steel, for other concrete structure and so on, then you will be using hard X-ray. Now as I was saying that these X-rays which are coming out, we happen to make the spectra of these X-rays. Spectra means what is the intensity of X-ray for a particular wavelength. That spectra was made. Let us make that, and then we will try to discuss why that spectra is coming up the way it is coming up. So let us make the spectra. If you draw the X-ray spectra, then on one side you will be plotting the intensity of X-ray, and the other side you will be plotting the wavelength of X-ray coming up. Let us suppose right now I am keeping the potential to be say 30 kilovolt. As I had said, this is also a kind of question which is asked, like what is the order of voltage? तो ये kilovolts में होती हैं, you understand? So let us suppose right now I am keeping it 30 kilovolt, and then I am trying to find out what is the intensity variation with wavelength. Then you will find a kind of graph something like this. You understand? This kind of graph which is showing the variation of intensity with wavelength, and this I have plotted for say 30 kilovolt. किलोवोल्ट एक्सेलरेटिंग पोटेंशियल के लिए हमने जो यहां पे इंटेंसिटी की वेरिएशन शो की है, इट इज लाइक दैट. यू कैन सी देयर इज अ काइंड ऑफ कॉन्टिन्यूअस प्लॉट ओवर विच देयर इज सम सुपर इम्पोजिशन ऑफ फ्लक्चुएशन ऑफ इंटेंसिटी at some particular wavelengths. Now let us suppose I am increasing this accelerating potential to, let us suppose, 40 kilovolt, and then you try to plot the same thing. Then you will find that the variation is coming out something like this. This is for 40 kilovolt. Understand? Again, if you try to see the kind of variation you have for intensity, overall again you have a continuous line over which there is a superimposition of some fluctuation of intensity, you can see. The very interesting fact is that the fluctuation of intensity is on the same wavelength. यहाँ पे आप देख सकते हैं कि जिस wavelength पे 30 kilovolt पे intensity ज़्यादा हुई है, on a higher voltage also you have the fluctuation of intensity on the same wavelength. You can see that. Here also again the fluctuations जहां पे भी हुई हैं 40 kilovolt पे भी lambda की same values के लिए fluctuation हुई है. The overall changes you see is that overall intensity, a kind of you can say continuous line that has come up. You understand? So in this particular spectra we have two different notations. एक जो ये continuous line आपको दिख रही है, that line we call continuous spectra. You understand? ये जो हमने पूरी इंटेंसिटी बनाई है, इसको हम दो पार्ट्स में डिवाइड कर रहे हैं. वन इज द कॉन्टिन्यूअस लाइन, चाहे यहां पे हो चाहे यहां पे हो. दीज टू कॉन्टिन्यूअस लाइन्स, दे आर कॉल्ड कॉन्टिन्यूअस स्पेक्ट्रा. नाउ वी विल हैव टू एक्सप्लेन व्हाई यू आर गेटिंग वेरिएशन लाइक दिस. एंड सेकेंड, शार्प जंप्स विच यू सी, जिसने अपनी लैम्डा की पोजीशंस नहीं चेंज की है डिस्पाइट द फैक्ट दैट द एक्सेलरेटिंग पोटेंशियल दैट इज चेंज, उन स्पेक्ट्रा के लिए हमने दूसरा नाम रखा हुआ है विच यू कॉल कैरेक्टरिस्टिक स्पेक्ट्रा. अंडरस्टैंड? ये दो स्पेक्ट्रा हमने इसमें डिमार्केट किया हुआ है. एंड नाउ वी हैव टू अंडरस्टैंड द मैकेनिज्म दैट व्हाई this kind of continuous and characteristic spectra are coming up. Now let us talk about the explanation to continuous spectra. Let us talk about the explanation to continuous spectra. Which spectra is the continuous one? यहां पे ये जो continuous line आप देख रहे हैं for 30 kilovolt, or maybe this continuous line which you are seeing at 40 kilovolt, they are being called continuous spectra. And इसकी explanation के लिए एक single German term understand, this is a single German term which was given to explain the continuous spectra. If you understand the English meaning of this, this means breaking radiation. You understand? The reason for continuous spectra was given as breaking radiation. या कहिए आप कि continuous spectra को हम breaking radiation भी कहते हैं. What is the meaning of this breaking radiation? Now see, जो आपने ये टारगेट बनाई थी, इस टारगेट पे these electrons are coming up, and you see these electrons have energy because you are accelerating them at some potential. जैसे किलो वोल्ट में आपने इसको एक्सेलरेट किया था, you understand, किलो वोल्ट से आपने इसको एक्सेलरेट किया था. Now tell me what is the energy with these electrons? इन इलेक्ट्रॉन्स में जो एनर्जी है that is charge into potential difference through which they are falling. यहां पे पोटेंशियल V है, यहां पे पोटेंशियल 0 है, तो दे आर कमिंग अप विद दिस मच एनर्जी. नाउ आफ्टर हिटिंग द टारगेट व्हाट विल हैपन? दीज इलेक्ट्रॉन्स in the worst case will be absorbed by the target. In that particular case you can say the entire energy of that electron will be lost. Now where is that lost energy? That lost energy comes out in the form of radiation. In maximum cases what will happen, that these electrons when they are hitting the target, they will not be losing the entire energy, rather a part of that EV that will be lost. But in any case, if this energy is coming out in the form of radiation, then you can say that the minimum wavelength which these electrons have the tendency to produce, that will be EV is equal to hc by lambda. You understand? अगर ये इलेक्ट्रॉन अपनी सारी एनर्जी लूज करेगा तो दैट विल बी द मैक्सिमम एनर्जी लॉस्ट, एंड इन दैट केस the wavelength which will be produced, that will be the minimum wavelength, as you can see from this equation. For rest of the energy loss, this wavelength will be more, and from here you can say that the value of lambda minimum can be written as hc by ev. What is this h? H is Planck's constant. This c is speed of light in vacuum, that is 3 into 10 power 8 meter per second. This E is electronic charge and V is the accelerating potential. Now for the sake of simplicity and from exam point of view, if you want to quickly solve the questions, then I will suggest that you should remember the direct value of this hc by E. And if you see that it is not so difficult to remember, you can easily remember 12400, very easy number to remember, angstrom upon the accelerating potential. Understand? अगर मान लीजिए कि हम इसको 12.4 किलो वोल्ट से एक्सेलरेट कर रहे हैं, तो जो वेवलेंथ एक्सरे की प्रोड्यूस होगी, इफ दैट इज सेम पोटेंशियल, तो 1 एंगस्ट्रॉम की एक्सरे प्रोड्यूस हो जाएगी. यू अंडरस्टैंड? अप्रोक्सीमेटली अगर हम 25 किलो वोल्ट से एक्सेलरेट कर रहे हैं इन इलेक्ट्रॉन्स को, तो यहां पे क्विकली आपको कैलकुलेशन करनी आनी चाहिए that will be 0.5 angstrom. You understand? This is the kind of calculation that will be helping you. Now once I have written down this formula and the easy value to remember, now try to fit this particular expression into the continuous spectra you have. Now let us try to explain this. Here you see the very interesting fact is that, let's suppose you are talking about 30 kilovolt, then you can see there is some sharp minimum value of lambda below which there is no emission. आप देख सकते हैं कि जो लैम्डा की बिगिनिंग हुई है वो कुछ एक वैल्यू के बाद हुई है, एंड दिस लैम्डा, दिस इज द लैम्डा मिनिमम जिसकी एक्सप्रेशन आपने अभी डिराइव की है 12400, upon voltage एंगस्ट्रॉम. बिकॉज हमने कहा था कि it will be very difficult that the entire energy of the accelerating electron is lost after the collision. तो अगर इलेक्ट्रॉन अपनी सारी एनर्जी लूज करता है तो ये वेवलेंथ प्रोड्यूस करेगा. बट इन केस इट इज नॉट इन ए पोजिशन टू लूज द इंटायर एनर्जी विच विल बी द नॉर्मल केस, देन इधर की वेवलेंथ प्रोड्यूस होगी, क्योंकि अगर एनर्जी कम होगी तो वेवलेंथ प्रोड्यूस विल बी मोर. अंडरस्टैंड? बिकॉज पोटेंशियल के आप देख सकते हैं इनवर्सली प्रोपोर्शनल है, तो सारी एनर्जी अगर का लॉस नहीं हो रहा है तो वेवलेंथ ज्यादा प्रोड्यूस होगी. एंड दैट इज वाई यू कैन सी इंटेंसिटी हियर इज वेरी स्मॉल, बिकॉज the probability of losing the entire energy, that is very less compared to the energy getting lost in some partial manner. तो अगर ये partial energy lose करेगा तो wavelength ज्यादा होगी and it can continue up to infinity. अगर wavelength की बातें करें तो यहाँ पे सारे wavelength की rays produce होती हैं, but X-rays के लिए हमने एक limit choose कर रखी है, say around 0.1 angstrom to 100 angstrom. इस range की जो rays हैं उनको हम X-rays कह रहे हैं, but यहाँ पे wavelength infinity तक produce होगी. On the similar line you can see why this sharp cut has shifted to the left side when you increase the potential. Now you can explain it very well, because you can see the lambda minimum, it is inversely proportional to the accelerating potential. So that is quite natural that when you are increasing the accelerating potential from 30 kilovolt to 40 kilovolt, then the sharp minimum cut of the wavelength that will be shifting to left side, as you can see here. But overall variation of the intensity that will be following the same pattern, because again the electron will not be in a position to lose the entire energy, rather a part of it, because of which आपकी variations इस तरह की होंगी. And overall जब आप accelerating potential increase कर रहे हैं तो जो intensity X-ray की हो रही है वो भी हमारी ज्यादा हो रही है. Maybe the number of electrons that is coming up that is large, and because of which intensity जो है वो ज्यादा हो रही है. So this was the explanation to continuous spectra, and for the sake of solving question, remember that this formula will be of great help, in which you have to directly substitute the value of potential and you can get the value of minimum wavelength, that is starting on the continuous spectra. Now coming down to the second part, that why you have sharp jumps superimposed on this continuous spectra. So let us try to explain the characteristic spectra. Let us now try to explain the characteristic spectra you have. The characteristic spectra was first explained by a scientist named Moseley. Now, to understand the characteristic spectra, try to look into the target. जो आपने molybdenum target choose की हुई है, if you try to see the microscopic view of the molybdenum target, what do you see? There will be the nucleus, then you will have K shell, then you will have L, then you have M, N, and so on. Understand? The way you had the energy levels in hydrogen spectra, N is equal to 1, N is equal to 2, and so on. So these are the names of the shells K, L, M, N, and like. Now here you have 2 electrons. अगर मैं K शेल को पूरी तरीके से यहां पे बनाऊं तो you have 2 electrons here. So these are the 2 electrons. On the similar line अगर आप L शेल को बनाएंगे तो there are 8 electrons, then 18, and so on. Now inside this target you have the electrons coming out from outside, isn't it? आपने टारगेट को एक्सटर्नल इलेक्ट्रॉन से बॉम्बार्ड किया है. Now these electrons will have the tendency to knock off the electrons. Knock off means ये collision के बाद यहां से electrons को अपने साथ लेके जाएंगे and target के अंदर जो भी atoms हैं से molybdenum के, तो उसमें एक gap create हो सकता है because let's suppose this electron is coming and here the gap is created. It is not essential that gap is created only in K shell. Maybe the gap can be created in L shell. And since there are number of atoms, तो कई सारे atoms की K shell में gap create होगा, कई सारी atoms की L shell में gap create होगा. Now to fill these gaps, electrons can come from the higher level. As you have in the hydrogen spectra, आपने देखा था n is equal to 1 तक ऊपर से electrons fall कर रहे हैं, from n is equal to 2, from n is equal to 3 and so on. So here also इस गैप को फिल करने के लिए अगर L के इलेक्ट्रॉन आ गए दैट इज फाइन, अगर M के आ गए, N के आ गए. सो नाउ सी बिकॉज ऑफ दीज जंप्स रेज निकलेंगी. सिंस दीज रेडिएशंस आर कमिंग आउट बिकॉज द इलेक्ट्रॉन्स हैव जंप्ड अप टू K शेल, तो इसलिए आप इनको K एक्सरे बोलते हैं. और उस पर से भी फर्स्ट लाइन को अल्फा लाइन, सेकेंड लाइन को बीटा लाइन, थर्ड लाइन को गामा लाइन एंड सो ऑन. You understand? Now, in case the gap is created not in K shell, rather in L shell, then you can say that to fill these gaps, the electrons come from higher level. So these X-rays will be called L X-ray because this has been produced to fill the gap which has been created in L shell, and accordingly again you can give the name L alpha, L beta and so on. You understand? In case you redraw this, then you can imagine it something like Lyman series and Balmer series. If it is K shell, this is L, then you will say that the lines are larger in K shell, lines are lesser in L, and what is this length related to? अगर आप देखें तो ये लेंथ जितनी ज्यादा होगी एनर्जी वैल्यू उतनी ज्यादा होगी, इसीलिए इनकी वेवलेंथ जो है वो भी कम होगी. यू अंडरस्टैंड? तो ये K एक्सरे के लिए हो गया. दिस लाइन इज फॉर L एक्सरे. नाउ ओवरऑल इफ आई आस्क यू किसकी वेवलेंथ कम है, किसकी वेवलेंथ ज्यादा है, देन यू शुड कीप इन द माइंड ये एनर्जी डिफरेंस है. K एक्सरे में आप देख सकते हैं एनर्जी डिफरेंस ज्यादा है, सो नेचुरली वेवलेंथ क्या होगी, लेस होगी. नाउ दिस एक्सप्लेन्स दैट दीज टू लाइन्स विच यू हैव हियर, दिस इज फॉर K एक्सरे एंड दिस इज फॉर L एक्सरे. दीज टू जम्प्स विच यू सी, ये K एक्सरे के लिए, ये L एक्सरे के लिए. वाई? बिकॉज K एक्सरे की वेवलेंथ आप देख सकते हैं कम है और L एक्सरे की वेवलेंथ ज्यादा है. Now try to explain why the position of this K and L X-ray has not changed despite the change in accelerating potential. Now see, these energy levels, they are the characteristics of the target on which the electrons have been bombarded, isn't it? ये जो energy levels हैं ये किसकी characteristics हैं? जो इलेक्ट्रॉन बाहर से आ रही हैं उनकी characteristics नहीं है. These are the characteristics of the target which you have taken. जैसे आपने यहां पे एक टारगेट लिया हुआ है तो उनकी एनर्जी लेवल्स फिक्स हैं. नाउ बाहर से जो इलेक्ट्रॉन्स आ रही हैं वो नॉक ऑफ कर रही हैं इनको. नाउ इन केस द इलेक्ट्रॉन्स आर कमिंग विद लार्जर स्पीड देन ऑल्सो इट इज गेटिंग नॉक्ड ऑफ. इफ इट इज कमिंग विद लेसर स्पीड देन ऑल्सो इट इज गेटिंग नॉक्ड ऑफ. बट बिकॉज ऑफ द चेंज इन द स्पीड ऑफ द एक्सेलरेटिंग इलेक्ट्रॉन्स, द वैल्यू ऑफ दीज एनर्जी लेवल्स दैट इज नॉट चेंज्ड. यू अंडरस्टैंड? ये एनर्जी लेवल्स जो हैं वो तो टारगेट की प्रॉपर्टी है. सो यहां पे एनर्जी लेवल्स के जो आप डिफरेंस देख रहे हैं that is not getting changed by your accelerating electrons. इसीलिए जब ये एनर्जी लेवल्स फिक्स हैं, सो नेचुरली इनसे जो रेडिएशंस आएंगी उनकी वेवलेंथ भी फिक्स होगी, एंड दैट इज व्हाई देयर पोजीशंस आर फिक्स्ड. बिकॉज हॉरिजॉन्टल एक्सिस पे आपने कौन सी क्वांटिटी प्लॉट कर रखी है, हॉरिजॉन्टल एक्सिस पे आपने वेवलेंथ प्लॉट कर रखा है. सो वेवलेंथ की पोजीशन नहीं शिफ्ट हुई. यू अंडरस्टैंड? बिकॉज चेंज इन एनर्जी का फॉर्मूला आप यूज करते हैं hc by लैम्डा, isn't it? तो अगर ये चेंज इन एनर्जी फिक्स है तो लैम्डा की वैल्यू फिक्स होगी. नाउ इफ यू ट्राई टू सी दीज प्लॉट्स माइक्रोस्कोपिकली देन यू कैन सी इवन इन K एक्सरे you have several jumps. Now all these jumps are फॉर डिफरेंट लाइंस यू हैव, जैसे आपने K में भी अल्फा बीटा गामा ऐसे कर रखा है, isn't it? K alpha, K beta, K gamma, these are the names you can provide. Now out of this alpha, beta and gamma, if I demand, then you can see the line alpha is the smallest one, therefore the wavelength here, that will be the largest one. So out of these three, in case I demand which one is for K alpha, which one is for K beta, then you can say the rightmost line will be for K alpha, next to that will be K beta, next to that will be K gamma. You understand? On the similar line, अगर यहाँ की sharp jumps देखें तो यहाँ पे L alpha will be the rightmost line, then you have L beta, then you have L gamma line like this. Now you understand कि क्यों हमारे यहाँ पे sharp jumps आ रही थी and sharp jumps की position क्यों नहीं shift हो रही थी, because they were the characteristic property of the target, and suitably we have given the name characteristic spectra because this is the characteristics of the target you have taken. Now Mosley gave the numerical relation as well for these spectra based on the Rydberg formula. अगर आप Rydberg formula याद करें तो उसके बेसिस पे हमने यहां पे एक फॉर्मूला दिया था आपको 1 by lambda. If you remember, Rydberg's formula was 1 by lambda is equal to R Z square 1 by N1 square minus 1 by N2 square. If you remember. Now try to think on the similar line. Here also this particular expression was getting used to explain Lyman series, Balmer series. So on the similar line, Mosley used this particular expression to give his expression of the characteristic spectra. In case you talk about the K X-ray, if you talk about K X-ray, then you see he said that square root of frequency, this is proportional to Z minus 1. Understand? For K X-ray, the kind of formula Mosley gave, that was square root of frequency is proportional to Z minus 1. Now in the Rydberg's formula, as you have 1 by lambda proportional to Z square, so you can say frequency is proportional to Z square, and square root of frequency now becomes proportional to Z, but instead of Z it is proportional to Z minus 1. Now why this Z minus 1? So long as the overall square root and proportionality is concerned, of course it is on the basis of this Rydberg formula, isn't it? यहाँ पे अगर आप देखें, अगर lambda को आप numerator में लेके जाएंगे तो that will become frequency, and this frequency becomes proportional to Z square. So based on that, उन्होंने square root of frequency proportional to Z लिखना चाहिए था. But instead of Z, he has written down Z minus 1. The reason is that this particular formula, if you have, it is related to hydrogen spectra, or you can say hydrogen-like atoms. What is the meaning of hydrogen or hydrogen-like atoms? You have a single electron there. तो वो single electron जब ऊपर से नीचे jump कर रहा है, then in the nucleus the kind of total charge it is finding, that is equal to Z. But here, when these electrons from higher level, they are coming up to K level, you can see that here maybe the charge on the nucleus is Ze, but what about this electron left over in the K shell? आपके K shell में शुरू में कितनी electrons थी? 2 electrons थी. उनमें से एक electron को आपने knock off कर दिया. Now this second electron is still revolving around the nucleus, and as you have studied the term screening effect or shielding effect, आपने screening constant की values भी निकाली है. If you try to see the nucleus from the point of view of those electrons which are jumping from higher level, they will find that there is a nucleus of positive charge Ze, and the negative electron that is encapsulating, क्योंकि इलेक्ट्रॉन जब रोटेट करती हैं तो आप समझते हैं कि वो एक क्लाउड की तरह उसने न्यूक्लियस को कवर कर रखा है. So for outside electrons, it will appear as if the nucleus has positive charge Ze and the negative 1 charge of electron. So overall, what is the net charge existing on this nucleus? Z minus 1, isn't it? That was the reason that he used the term here Z minus 1 for defining the K X-ray. Now based on that, in case you have to compare, अगर आपको दो अलग अलग टारगेट्स की फ्रीक्वेंसी ऑफ एक्सरे को कंपेयर करना है, देन यू कैन ऑलवेज से स्क्वायर रूट ऑफ f1 अपॉन स्क्वायर रूट ऑफ f2 दैट इज इक्वल टू z1 minus 1 अपॉन z2 minus 1. This is a kind of formula you can use. And in general, say you have L X-ray and so on, you should note that this square root of frequency that will become proportional to some constant Z minus some other constant. So let me write down that formula here. In general, the square root of frequency will be some constant A into Z minus B. प्रोपोर्शनैलिटी साइन अगर आपने रिमूव कर दिया है तो ये कांस्टेंट A उसका वर्क करेगा, एंड अगर ये K एक्सरे होगी तो B जो स्क्रीनिंग कांस्टेंट की वजह से आ रहा है, दिस B विल बी हैविंग द वैल्यू 1, बट इन केस लेट अस सपोज दिस इज ट्रू फॉर L एक्सरे, then the value of B will be changed. It will not be 1, rather it will be around 5.9, but that is not your concern because we will be talking about the questions in which the proportionality will be coming into picture, and if at all the constant is required, we will be providing you in our questions. So that explains the characteristic spectra, and naturally the Moseley's relation is explaining the characteristic spectra, and the breaking radiation concept is explaining the continuous spectra. Understand? Now let us one by one discuss the kind of concepts involved here. What happens if you are changing the target? What happens if you are changing the accelerating potential? So these are the concepts now you have to discuss so long as these two spectra are concerned. So let us talk about that. Now note that when the accelerating potential is changed, then only the continuous spectra is changed. You understand? जब आप एक्सेलरेटिंग पोटेंशियल को चेंज करते हैं, देन ओनली द continuous spectra is changed, but when the target is changed, understand? आपने अब let us suppose टारगेट चेंज कर दिया, पहले आपने एक्सेलरेटिंग पोटेंशियल चेंज किया, then we see that continuous spectra is changed, but when the target is changed, then the continuous as well as the characteristic spectra are changed. Understand? When the target is changed, then the continuous as well as the characteristic spectra, that means both the spectra are changed. Now my question is why? ऐसा क्यों हुआ कि अगर आपने एक्सेलरेटिंग पोटेंशियल चेंज किया तो सिर्फ कॉन्टिन्यूअस स्पेक्ट्रा चेंज हुई है, लेकिन जब आपने टारगेट चेंज कर दिया तो दोनों ही स्पेक्ट्रा चेंज हो गई. यू सी दिस पर्टिकुलर थिंग इज रिलेटेड टू द फैक्ट दैट एक्सेलरेटिंग पोटेंशियल, जैसे आपने देखा था कि E into V, isn't it? That was hc by lambda. This was explaining the continuous spectra. तो जब आप एक्सेलरेटिंग पोटेंशियल चेंज करेंगे, सो नेचुरली द ब्रेकिंग रेडिएशन विल बी चेंज्ड, जो लैम्डा मिनिमम होनी चाहिए, दोज थिंग्स विल बी अफेक्टेड. बट यू सी, टू चेंज द कैरेक्टरिस्टिक स्पेक्ट्रा यू हैव टू गो इनसाइड द टारगेट. टारगेट के अंदर के स्ट्रक्चर को जब तक आप चेंज नहीं करेंगे तब तक कैरेक्टरिस्टिक स्पेक्ट्रा चेंज नहीं होगी. दैट इज व्हाई एक्सेलरेटिंग पोटेंशियल कुड नॉट चेंज द कैरेक्टरिस्टिक स्पेक्ट्रा. But why the change in the target has changed both of them? Now see, target अगर आप change करेंगे तो this is a fact that the inside energy levels they are changed now. So the position of the intensity for characteristic spectra that will be changed. क्योंकि energy level change हो गई तो naturally delta E is equal to hc by lambda, isn't it? And अगर एनर्जी लेवल्स चेंज हो गई क्योंकि टारगेट चेंज हो गया है, सो नेचुरली वेवलेंथ की जो पोजीशन होगी वो भी चेंज हो जाएगी. बट इट ऑल्सो डिपेंड्स दैट द न्यू टारगेट वेदर इट इज सॉफ्ट और हार्ड, इन द सेंस जो बाहर से इलेक्ट्रॉन्स आ रही हैं उनका टारगेट के साथ कोलिजन हो रहा है. नाउ द डिग्री ऑफ इनइलास्टिसिटी विच इज प्रोवाइडेड बाय द टारगेट दैट इज ऑल्सो चेंज्ड. अगर टारगेट सॉफ्ट होगा देन मे बी इलेक्ट्रॉन्स ज्यादा से ज्यादा उसमें एब्जॉर्ब होने की टेंडेंसी होगी एंड मोर यू कैन से लोअर वेवलेंथ इंटेंसिटी एक्सरे विल बी प्रोड्यूस्ड. बट लेट्स सपोज न्यू टारगेट जो आपने ली है दैट इज हार्ड, इलास्टिसिटी वैल्यूज मोर, then in that case electrons will not be losing their energy, rather after hitting it they will be reflected with considerable amount of energy. That means the energy loss is not very high, and in that case wavelength jo produce hogi that will be on larger side, so intensity variation that will be different. So that explains that why apart from characteristic spectra the continuous spectra as well is changed when you are changing the target. You understand? Dono characteristic as well as continuous spectra will be changed when you are changing the target, but it's only the continuous spectra that will be changed when you are changing the accelerating potential. Now based on that, let me ask you a question.